one of the very last things that we covered in our previous session was these two diagrams. In fact, we haven't gone into too much detail yet, but we must certainly remind ourselves that, and it is a great thing about this book, where to continue singing its praises, it starts off with the simple case. So what made this so simple? It's looking at a single predictor variable with two classes. So the probability depends on in which class you find yourself in. So the probability of X given a class Y. So our probabilities are measured in terms of area. So maybe this probability, this area, whereas when we now work with more than a single predictor variable, we will have volume representing area or higher dimensional concepts. So this shaded, can't believe why I'm finding it so difficult to shade this. So this region, what does this region represent? This region represents the probability that the predictor variable is between these two values, given that y is k, given that y is this green, or the class represented by this green. Probability density function. That's quite an important acronym. PDF. PDF, not the extension of Adobe documents, but probability density function. We have this green probability density function. For all intents and purposes, it gives you the histogram concept from secondary school. And we're looking at a conditional probability where we're taking the probability that X is a specific value given that Y is this green class. This is then used in Bayes' theorem being this one. The red is these FKs. These FKs, these FLs. And what Bayes' theorem does is this expression swaps the conditionals around to produce what we are in fact after. That is the probability that Y is of a specific class given, in this easiest scenario, given that X is a single characteristic, height, you name it, and then the number of books that you have in your room, the number of hours that you go to the gym, just a single characteristic. And we saw that in practice, you wouldn't have the parameters of these classes. You wouldn't have the true mean of each class. You wouldn't have the true variance of each class. Instead, you estimate them using what is the LDA method. Once you have these, then you can make your calculations and you can create this is it a decision line? What is it? It is a decision boundary. Now, with more than two variables, more than one predictor variable, so with two or more predictor variables, in the case of p equals 2, you'll have these probability density functions that are not curves, but are surfaces. Now, if you had more than two, as is very often the case, if you're looking at more than two characteristics of each observation, then you have objects in higher dimensional space. This is the formula that generalizes the normal distribution, the Gaussian distribution. Pivotal to its algebraic description is this covariance matrix. It's a square matrix. You calculate its determinant to scale the volume down to 1. Remember, in this case, the volume under the surface represents the probability. So the total volume has to be 1, just like the total area over here has to be 1. You'll get that 1 by using the square root of the determinant, and you'll get a real number over here by multiplying 1 by p by p by p by p by 1. If you perform these two multiplications and multiply by -1/2, you'll have a single real number. So for each class, we're assuming a multivariate Gaussian distribution with mean mu k, that would be a vector, and covariance matrix uppercase sigma. We do the same thing as in the previous section. We calculate these delta k's for each. So x is a vector. It's the one thing I wish the book would do. Just distinguish between real numbers. They're obviously expecting us to just interpret depending on the context, but you give it your input characteristics. So, for example, it depends on what you're modeling, right? Whatever. And then for each class, you will calculate delta k of x. The class that gives you the largest delta k of x will be the class into which you will classify the observation with the x characteristics. And we're seeing that over here. As always, the book has more information than you would really have in real life. And what do I mean by that? The book knows the true mean of each class, mu green, mu orange, mu blue, and it also knows the true covariance matrix, which is why it has the dots, I think, are the true decision boundaries, and the solid lines are what you would get in real life based on not the full extent of information, but with a couple of simulations from each one. Of course, in real life, it works backwards. You have the observations, so you know that you have a couple of x1, x2s. That's your input. Okay, your x1, x2 is your input. The colors are your outputs. So you know that, for instance, you've observed one data subject in your training data, the specific data subject would have three pieces of information. Its x1 is 2, whatever that 2 is, could be you name it, bank savings. The x2 is 0, again, pick your variable of choice. And then your data set is also telling you it is a blue data subject, where blue could be a type of sickness, for instance. There's a lot of theory now over here. I wonder if we can do without it. Yeah, it just keeps on going and going and going. So this is probably all important. Let's see. Are we towards the end of the chapter? Yes, because now we're in labs. Should we just... It's not too many pages. We would probably finish them within one session. But I don't know about everyone else, but I can definitely say I am feeling the fatigue now that we're towards the... I mean, somehow we're already on page 144, and we haven't skipped too many sections. Why don't we see how far we get by working in R? Let's see. So section 4.6, lab, towards the end of this chapter, logistic regression, LDA. So in fact, we've only done these two, right, till now. And then there's QDA, and that must be K nearest neighbors. Let's start with 4.6.1, the stock market data. We will begin by examining some numerical and graphical summaries of the S market data. Now, if we're even going to do this, it does assume that we actually have access. Let's check. So what do? We do library, we do ISLR, now we do data, S market, and that seems to have worked. And if you want to look at like this, and these are, this is our data set. And we're probably going to predict the direction if a stock goes up or down. We have 125 observations. We have year, lag 1, lag 2, lag 3, lag 4, lag 5, volume, and today. So the lag is probably the movement, if I had to guess, is probably the movement over the past 5 days. Let's have a look. So if you go into packages, you type ISLR, I said type ISLR, and we click S market. Apologies if the text isn't too large. Daily percentage returns for the S&P 500 stock index between 2001 and 2005. Okay, so we're not looking at specific stocks. We're looking, you are familiar, right, with the S&P 500. Let's get just a quick explanation. It's the 500 largest companies listed on stock exchanges in the United States. So multiple stock exchanges. Think of New York Stock Exchange. Year. The year that the observation was recorded. So 1 second. Let's just... So this is our data. We have 2001, 2001, 2001. What's this exactly? The percentage return for previous day, percentage return 2 previous days, 3 previous days, 4 previous days, 5 days previous. The volume of shares traded, number of daily shares traded in billions. So just the selling and buying that's going on. Today, percentage return for today, direction, a factor with levels down and up, indicating whether the market had a positive or a negative return on a given day. So that just depends on today, doesn't it? I think. If these are positive, then we're just saying up. Okay. Okay. This data set consists of percentage returns for the S&P 500 stock index over 1,000 to 150 days from the beginning of 2001 until the end of 2005. So just to make sure, we have it's 5 years, isn't it? It's 5 years, and if I do times 365, that would give me 1825. Now I know I'm not allowing for leap years, but actually mine, why is mine larger? So 1 to 5 days. Okay, maybe we didn't record each specific day. Although it does say, for each date in the data set, I guess, we have recorded the percentage returns for each of the 5 previous trading days, lag 1 through lag 5. Again, if we just go into maybe like Yahoo Finance, just see how the S&P is performing. I don't even know the code. Is it SP500? Maybe just type 500. Yeah. Oh, yeah. We'll take these are indices that are kind of tracking. Let's take this one. And can we make this larger? Here we go. Let's see. Why aren't I seeing anything? So this is selected, isn't it? If necessary, we'll just go back to the previous page. So let's look at it, for example, from. Okay, this seems to have broken it as well. So this is 1 day, 5 days, 1 month. Now 6 months is where we lose everything apparently. So let's just keep it like this. Just think of it as you're taking the largest 500 companies, and for example, over the past day, and I shouldn't have clicked that because we get this again, and I can't seem to get this to work. Over the past day, it's in the value of, you need to think of them as like a basket of companies. The value has increased from this figure in the gray to this figure, and you've seen the percentage, change. I'm not entirely sure against what this is, but it's saying plus 95. I'm not sure if I guess that would be USD. Anyway, hopefully it just makes all this a bit more tangible. So for each date, we have reported the percentage returns. So really, is the price going up or is the price going down? For each of the 5 previous trading days, lag 1 through lag 5. Right. So would it make sense to say, if this is day number 2, this is just this, right? These 4, this these 4 are these 4, etc., right? Because you're just taking the next day. So for example, if day number 1 had these 5 as sort of like the 5 previous days, then when you go into day number 2, these are these, aren't they? So like what was for day number 1, what was 4 days ago for day number 1, for day number 2, that same day is 5 days prior to day number 2. So which is why you're seeing a lot of the data kind of repeat itself. For instance, what was today for day 1 is yesterday for day 2, right? Was the movement in the stock market, what was today for day 5 is what was yesterday for day 6. This is kind of the boring part of data science, but it's really good when you have your data set. But before doing anything, I mean, even not even secondary school sort of summary data. It's a good idea to just, does the data look like what you would expect it to look like? And we've can see that in the last few days. You can kind of see, okay, so up if today is positive, down if today is negative, and you start getting an idea. Otherwise, maybe I speak for myself, but I really feel like I can really easily get lost in the data, and I don't really know what I'm looking at. So yeah, you had quite a wild movement over here. Would you like if we took just the today? So we do S market today. So that would be just the column, just the values in the today column. And you can even get an idea of the way the stock market behaved by doing plot. Maybe 1 to 1250, and this. So this is the behavior of the S&P 500. We're not looking at any lags over here. So it was most volatile. You have a particularly volatile period over here. with daily returns. I mean, this is daily, right? 6% might not sound like a lot, but probably what we're hitting in terms of inflation right now on certain items. But these are daily returns, and remember, you're not looking at one company. In many ways, now very often the companies within the S&P 500 are highly correlated, especially in times of crisis. Their stock performance tends to move in one direction for each one. But these are daily, right? These are daily. So if you're seeing a -4% on the entire market on the top 500 companies in the US, which very often translates to top 500 companies globally, right? That's quite significant. So, World Trade Center, perhaps 2001, 2005, probably, right? I wouldn't be surprised if we're looking at 9/11 attacks over here. It would be more useful if we actually had the dates, but I haven't done it that way. Yeah, that makes perfect sense, right? Because it's starting in 2001 and 9/11. Well, actually, 9/11 would be maybe a bit more over here, right? Not quite. Let's have a look. We have also reported volume, the number of shares traded on the previous day in billions. Today, the percentage return on the date in question and direction, whether the market was up or down. Can you already start thinking of how you would use this data? Well, probably you want to be able to tell the model, maybe just the lags, maybe you just tell the model, this is what the stock market did these past 5 days. If it did this thing, then today, is it going to go up or is it going to go down? Let's see. I'm probably totally off, but these kind of, we trying to anticipate what's coming next is quite useful. Okay, so I think what I'll do is I'll share R, and I'll go through the code. So let's clear all this. And I'm not showing you what I'm saying in the book, but the first thing is we're doing names. Okay, so that's just the names of your variables. That's useful if you want to change the names in the data set. This is how you do it. You then reassign maybe a new set of names. Okay, we can look at the dimension, meaning 1 to 5 rows, 9 columns. Summary. This is your summary. So, for example, the greatest jump in prices was 5.7. The greatest decrease was 4.9. Market was down 602 of these days. Market was up 648. I mean, although this is numerical, it's more like categorical. It's more like qualitative, right? Just yours. And then you have the volume. Okay. This is shares traded. You're buying and selling. Okay. Then we have the core function. I'm not well, I could probably share. the core function produces a matrix that contains all of the pairwise correlations among the predictors in a data set. The first command below gives an error message because the direction variable is qualitative. So we're going to remove the last column to get rid of any qualitative data. So we're going to have core. We don't tell it S market. We tell it S market, remove the 9th column. And I would rather see that okay. So these are the correlations. What do we mean by correlation? It's just if it's a positive correlation, then between two variables. So let's take an example. Let's take, for instance, this, which, by the way, would be the same as lag 4 and maybe this one. Yeah, those two are the same. It's just lag 4 against lag 1. So they're over here they're negatively correlated, although it's probably a number quite close to 0. So in fact, probably statistically speaking, we're actually going to say that lag 4 and lag 1 are independent of each other. Yeah, as one would expect, the correlations between the lag variables and today's returns are close to 0. In other words, there appears to be little correlation between today's returns and previous days' returns, as you would expect. Otherwise, otherwise you'd be able to predict the market very easily. The only substantial correlation is between year and volume. Let's see. Year and volume. Oh yeah, it's an order of magnitude larger. Look. So that would tell you that as we travel in time, 2001, 02, 03, 04, 05, you expect that as the year increases, there was more trading activity, there were more shares that were purchased. By plotting the data, we see that volume is increasing over time. Okay, so let's do it. And the book just writes plot volume. Okay, so it's increasing over time. In other words, the average number of shares traded daily increased from 01 to 05. Right. Logistic regression. What was logistic regression? Yeah, logistic regression is when we're using logs and e to the, and we had to estimate the parameters using maximum likelihood. Next, we will fit a logistic regression model in order to predict direction using lag 1 through lag 5 and volume. Okay. Yeah, which is what we should expect, right? There's not much more you can do with such a model, with such a data set, excuse me. The GLM function fits generalized linear models, a class of models that includes logistic regression. The syntax, notice we're not using LM. In fact, it's the first time in this book you notice something is the first time because it's mentioned in the margins. It's the first time we're doing GLM. The syntax of the GLM function is similar to that of the LM, except that we must pass in the argument family equals binomial in order to tell R to run a logistic regression rather than some other type of generalized linear models. Okay. So did I stop sharing? Sorry about that. What are we going to type over here? We're going to write let's just give it a name. And the book calls it GLM fit, but this is just a name. If you give it a name, you're saving the object under this name. So GLM fit. We have our function GLM. We're going to give it the formula direction. Now this might not work because I haven't attached. You might need to do S-market dollar direction, just like I have in 9.7. Regressed on lag 1 together with lag 2 together with lag 3, lag 4, lag 5, and volume. Do notice that this is something that in the book we didn't quite do. Whenever we had the section on logistic, even the examples that beg your pardon. No, I was going to say that in the book we never use logistic regression for multiple predictor variables. That's incorrect. What the book didn't do was logistic regression for a response variable with more than 2 classes. This is in actual fact 2 classes, right? Either up or down. So in actual fact, this is consistent with the theory that we've been discussing. Now it needs to be based on the data, and we'll take the S-market data. We'll specify the family. The family is binomial. If you write binomial, then the compiler knows to fit the GLM based on the principles of logistic regression. Okay, I ran it. And now we look at the summary of the model that we've produced. Let's have a look. Let's have a look. These are the parameters. These are the parameters. And the Z scores are, the Z values are quite high. In fact, there are no asterisks. We're probably just going to conclude that these aren't very useful, as one would expect, I think. These aren't actually very useful in predicting if the market is going to be up or down. The smallest p-value here is associated with lag 1. Lag 1, smallest p-value. It's smallest, yeah. Quite high though. Usually you'd want nothing more than 0.05. The negative coefficient for this predictor suggests that if the market had a positive return yesterday, then it is less likely to go up today. However, at a value of 0.15, the p-value is still relatively large, and so there is no clear evidence of a real association between lag 1 and direction. We use the coefficient function in order to access just the coefficients, so the parameters, the betas. For this fitted model, we can also use the summary function to access particular aspects of the fitted model, such as the p-values for the coefficients. So what you do is, if you just want these coefficients, there's the coefficient function, just give it GLM fit, and that's those over there. Or else you could take this summary and treat it as sort of like a data set in of itself. And you do, for example, dollar, and you could do I'm copying it from the book. Coefficient, the fourth. So these are the p-values, right? Those are the p-values. With the highest one being for lag 1, the 0.15. Now this one's really useful. The predict function can be used to predict the probability that the market will go up given values of the predictors. The type equals response option tells R to output probabilities of the form probability y is equal 1 given x, as opposed to other information such as the log it. Okay, if no data set is supplied to the predict function, then the probabilities are computed for the training data that was used to fit the logistic regression model. Here we have printed only the first 10 probabilities. We know that these values correspond to the probability of the market going up rather than down, because the contrasts function indicates that R has indicated a dummy variable with a 1 for up. What do we mean by a dummy variable? What we mean is up and down, you usually give them 1s and 0s since it's qualitative. And I guess it's done automatically by R. And it's taking, in this case, it's taking up as 1. Now how would you know it's taken up as 1? Because you can actually ask R. If you give it contrasts, contrasts direction. Yep. This is because I haven't attached the data. I didn't get this error in the GLM code because you're kind of explicitly telling it over here. Take your data from S market. Whereas over here, there isn't enough information for the compiler to tell what that direction data is. But if you do it like this now, so don't ask me why or how R decides, but up is 1 and down is 0. Yeah, so the predict function, we can now give it So now that we have a model, and you have a model as soon as you've decided to use logistic regression and estimated your coefficients over here. Now you could do it manually. You could create. Remember, please do remember that what we're creating is just this expression, but with more than just two parameters. Yeah, this is exactly it. This is exactly it. So you've estimated the intercept, and then for lag 1 up to lag 5, and the volume. So you could type this expression manually into R now that you have your beta estimates. A much quicker way is the package just does it for you. All you tell it is predict. Predict. Let me go back to the page. Where were we? Logistic regression. I'm not sharing right now. I'm not sharing the book. GLM fit type response. So you tell it, hey, listen, GLM fit, which is just the coefficients that we estimated. And if you type response, let me see. Yeah, these are all the different probabilities. We'll do GLM. Let's see the first 10. Yeah. These are your first 10 probabilities. If you want to look at what they, sorry, just a bit tired today. GLM, no, S market. We'll do the first 10. And over here, we'll calculate. So look. I mean, given that there probably isn't that much of a relationship between the predictor variables and the response, most of these probabilities are just around 50%. So the model really is telling you it's a 50-50 chance. So it's anyone's guess. But anyway, this is how they compare against the actual training data. Again, it's not very useful. It's not very useful just because we really shouldn't expect this data to really give any insight into how the market is going to perform. In order to make a prediction as to whether the market will go up or down on a particular day, we must convert these predicted probabilities into class labels up or down. The following two commands create a vector of class predictions based on whether the predicted probability of a market increase is greater than or less than 0.5. And I think we should, I'm sorry, I'm yawning. I think we should emphasize, we are choosing this 50%. So we're just saying, okay, model is giving us all these probabilities. How are we going to translate them into up or down? Well, let's just say anything above 50%, then we'll interpret the model as telling us up, Everything else, the model is down. And let's see. Let's see. So, right. What are we doing in this line? Let's put them next to each other. Sometimes I think maybe doing 1 hour doesn't really do, while useful, maybe it's not, maybe we could benefit from longer sessions. But I appreciate how difficult it is for all of us to even fit 1 hour in. Let's see. So what are we doing? Well, we created these probabilities. Let's call them GLM predict. Not just the first 10. I want. So those are the first 1,000 predictions, courtesy of our model. I always forget how to remove the header of these vectors. Probably been a bit more useful without them. But anyway, 0.51, 0.48. So we have a vector of 1250 values. Is this vector over here, GLM. Oh, the book doesn't want me to call it that. The book wants GLM probability. So we have a prediction for each observation in our training data set. Of course, the question is, the values or the movements that the model is predicting, are they even in line with the training data set? Okay. We're now going to create a second vector. GLM predict is rep. I think this is just repeat and down 1250. So initially we just have this vector. This is just our first step. It's just all downs. But now what we're going to do is this. We're going to say take all these downs and compare to the probabilities that the model is producing, and where that probability is greater than 0.5, assign up. Right. So I think there are two things that we need to understand. Number one, what are we trying to do? And number two, the syntax that we're using. What we're trying to do, I think, is straightforward. You started with just because it's easy to do it this way. You just have a vector populated with one data type, not data type, data entry down, 1250 downs. Now the syntax. Now the idea is that in actual fact, some of those downs need to be up, depending on the model's probability predictions. And we're saying, take all your downs. But those downs that actually sort of have the same position as when the probability is greater than 0.5, replace them with an up. So this is what we now have. We have ups and downs. The first command creates a vector of of 1, 2, 5, 0 down elements. The second line transforms to up all of the elements for which the predicted probability of a market increase exceeds 0.5. Given these predictions, the table function can be used to produce a confusion matrix in order to determine how many observations were correctly or incorrectly classified. So we'll do it in R, but the idea is your predictions, your model's predictions, based on that 50% cutoff against the actual training data that we used to fit the model in the first place. Okay. Now, which ones did we get right? We only got these right. We only got these right. Why do I say that? Because the direction had 1, 4, 5 downs that were correctly classified as down. And the direction data had 507 ups that were correctly classified as up. In fact, this is what the book goes on to say. The diagonal elements of the confusion matrix indicate correct predictions, while the off-diagonals represent incorrect predictions. Hence, our model correctly predicted that the market would go up on 507 days and that it would go down on 145 days for a total of 652 predictions, which is not very good, is it? We only got just over half of them correct. And that 2.2% above half, that's probably just sheer luck. The mean function can be used to compute the fraction of days for which the prediction was correct. In this case, logistic regression correctly predicted the movement of the market 52.2% of the time. Yeah, it's no fault of logistic regression. The point that the book is trying to make is that sometimes the data that you have just isn't that helpful for making predictions. At first glance, it appears that the logistic regression model is working a little better than random guessing. However, this result is misleading because we trained and tested the model on the same set of 1250 observations. In other words, 100 minus 52.2 is 47.8% is the training error rate. As we have seen previously, the training error rate is often overly optimistic. It tends to underestimate the test error rate. In order to better assess the accuracy of the logistic regression model in this setting, we can fit the model, and this is standard procedure over here. You fit the model using part of the data, and then examine how well it predicts the held out data. this will yield a more realistic error rate in the sense that in practice, we'll be interested in our model's performance, not on the data that we use to fit the model, but rather on days in the future for which the market's movements are unknown. So it's actually really interesting example. Yeah, and a lot more to say. I don't regret taking this approach. It fit perfectly in this 1 hour. And I'm going to stop over here.